Hi guys, so this is the second part of the first lesson. This kind of goes along with the counting video. This lesson is going to be about permutations and combinations. The first example I'm going to do is an example of permutations. So what I have drawn here are 6 balls, numbered 1 through 6. And you can imagine they're not in any sort of order right now. This is just a collection of balls sitting around. And the question is, how many ways can I arrange the balls? So we're going to make an arrangement, and this will be the first ball, the second ball, the third ball, the fourth ball, the fifth ball, and the sixth ball. And let me just pick a ball at random. Say I pick ball 3 to be the first ball. Referring to the last video, the first choice that I make you could think of as the first experiment. So this is like experiment 1. And the number of outcomes there are 6 outcomes. So I could have picked any one of the 6 balls, numbered 1 through 6. So last time in the counting principle, we had separate experiments. The example was we had an entree and a dessert that you could choose at a dinner. Here, we want to have a second experiment in which we're going to choose another ball, but the issue is I now cannot choose ball 3. It's already been chosen in experiment 1. So in experiment 2, I'm picking again from the same collection, but now that I can no longer use what I've used in experiment 1. So say in experiment 2, the next ball I choose may be ball 2. So I can no longer use ball 2. And notice that before I had chosen ball 2, before I exit, there were 5 balls without exits. I had 5 choices here. And then this continues on. So for experiment 3, I have 4 choices. So there's 4 choices, and maybe in this example, this specific example, I choose ball 5. So I put ball 5 here. For the fourth experiment, I have 3 choices. Maybe I choose ball 1, and so ball 1 is gone. For the fifth, I have 2 choices left. Say ball 6. And then finally, there's only 1 choice for the last thing, which I guess would be ball 4 in this case. So there's one arrangement of the balls. I could have arranged the balls 2, 3, 5, 1, 6, 4. I could have also arranged the balls 2, 1, 4, 3, 5, 6, or whatever. So this is a specific example. If we want to count all the ways that I could arrange the balls, then we can use our counting principle that we learned last time. So we have 6 experiments, experiments 1 through 6, and we just count the number of outcomes and multiply them together. However, we don't get 6 times 6 times 6 times 6, because whenever we choose among the 6 balls for the first experiment, that ball is removed, and so we have 5 balls remaining. And then in the second experiment, we can choose one of the 5 balls, remove that one, and then 4 remaining. So what happens is we end up with 6 times 4 times 3 times 2 times 1, which we call 6 factorial, which is what I think 720. So in general permutations, the number of ways to order n objects is n factorial, which you may or may not be familiar with that notation. So n factorial just stands for 1 times 2 times 3 and so on until you get to n. So for example, 2 factorial is 1 times 2, which equals 2. 3 factorial is 1 times 2 times 3, which equals 6. 4 factorial equals 1 times 2 times 3 times 4, which is 24. And since the factorial gives you the number of permutations of a set of n objects, you can imagine in a class like this we're going to be using factorials. So you'll want to get comfortable with that. One thing that might not be so obvious is 0 factorial. And it turns out that 0 factorial is defined to actually be 1, not 0. So that's one case you want to pay a little bit closer attention to. So that's essentially what permutations are, just the number of ways to order objects. The other topic I wanted to talk about really quickly was combinations. So let's run through a quick example here, too, to get the idea. So say we have 4 people who want to play a tennis match. We'll say Alice, Bob, Carl, and I don't know, Dana. Okay, so we've got these 4 friends. They're going to play a 2-on-2 tennis match. So we'll represent them by A, B, C, and D. We'll say they're all relatively equal players, and they're all friends. So they don't really care how the teams are divided up. How many possible teams could we make? So the question is, how many teams are there? Well, we could just look at the arrangements of the players. So one arrangement would be A, B, C, D. One arrangement would be B, A, C, D. Another may be A, C, B, D. And so on. So we look at them in every possible order, just like we did with the 6 balls. What orders can we make? And then let's just draw a line down the middle. So here this separates 2 players onto 2 teams. The first 2 players are on team 1, say, and the other 2 players are on team 2. So in the first example, Alice and Bob are on the team against Carl and Dana. And the second one, Bob and Alice are playing Carl and Dana as well. So what happened here, we ended up with the same teams. In the first team, it's Alice and Bob, and the second one, it's Bob and Alice. So really, we don't want to count these as different teams. These 2 should be the same. However, here we do see that we have a different one. So here's Alice and Carl versus Bob and Dana. So just looking at the permutations, as we just discussed in the previous example, there's 4 players, so the number of permutations is 4 factorial, which is 1 times 2 times 3 times 4, or 24. However, once we've picked players on the left, it doesn't matter how those are permuted. So notice that we can take A and B or permute them to B and A, whichever order. And for each one of those, we're going to count CD. And then likewise for A and B, we would count DC. And for B and A, we would count DC, and so on. So we want to cancel off the number of times we've counted the same team on the left-hand side. So we have 2 factorial. Since there's 2 symbols on the left side, there's going to be 2 factorial ways to arrange those. And there's also 2 on the right side. So we have 2 factorial ways to arrange the team on the right side. And so what we want to do is cancel that. So we're going to take 4 factorial and divide it by 2 factorial times 2 factorial, which is 24 divided by 2. So 2 factorial, remember, is 1 times 2 is just 2. 2 times 2, which equals 6. So after we cancel out all these redundancies in the permutations, we have 6 different ways to make teams. Now there's a special symbol for this as well, so this is going to come up often. So if we have n objects, like the 4 players, or they could be any sorts of objects. They might be cards or dice or something else. And we wish to choose k of them. the number of ways, or let's say number of outcomes possible is, and we make it the special symbol, n choose k, which is our n factorial over, and then there's k factorial ways to permute the k elements we did choose, and then n minus k permutations of the elements we did not choose. So for the previous example, we had n equals 4 players. We had team 1 equals k equals 2 players. And then team 2 was everyone else who wasn't on team 1. So team 2 was the n minus k, which is also 2. Because notice that this is 4 minus 2, which equals 2. So when we go to plug in this formula, 4 choose 2, we get 4 factorial divided by 2 factorial times 2 factorial, which equals 6. So that's how we compute that there are 6 different unique teams that we can make. Now, once again, this can be extended with basic induction. For those of you who've taken discrete math, maybe you didn't believe me when you were in the class, but I told you that concept comes up a lot. Let's see. Gotta check my time here. Okay. So suppose instead of breaking it up into 2 groups, we maybe wanted to break it up into 3 or more groups. So say maybe we have 10 people, and we need to make 3 committees. So committee 1 has 4 people. 2 has, say, 3 people. And 3 has 3 people. So how many ways can we make these 3 committees? Okay. Well, it's the exact same concept. We have 10 people. We can permute the 10 people in any way. So we have essentially 10 experiments, you can think. So this is the person 1, person 2, person 3. The first 4 people are on committee 1. The next 3 people are on committee 2. And the last, what did I do here? I can't count. 6, 7, 8, 9, 10. The last 3 people are in committee 3. So these are our committees. Once again, we're going to have 10 factorial ways to arrange all 10 people. But again, we don't want to count the same persons if we just permute them within one committee. So we have to divide out 4 factorial to cancel off the redundancies in the first group, 3 factorial for the redundancies in the second group, and then 3 factorial for the redundancies in the third group. So in general, if we have n objects, and we have k1 plus k2 up to km equals n, and we want to split these n objects into the groups of size k1, k2 up to km, then we have the formula n choose k1, k2 up to km. So we're going to make groups of these sizes, and that will just be done by the formula. The number of ways to do this, n factorial over k1 factorial, k2 factorial, and then you take the product down to km factorial. All right, guys, well, that's it for the first lesson. So God bless you, and I'll see you soon.